The particles in a liquid have enough energy to move out of their fixed positions, but not far enough to move like apart. So this would be good to remember because I may or may not ask a question about this later, where the particles in a liquid have enough energy to move out of their fixed positions, but not enough to move far apart. Okay, so this is, you guys should be pretty familiar with vapor. It's between like gas and liquid. Um, Vapor is a matter that exists in the gas state, but is generally a liquid or a solid at room temperature, and it's called vapor. For example, water. Water is a liquid at room temperature, thus water vapor is the term for a gas state of water. Just because like, yeah. So now we're going to talk about gases. Gases have no definite shape or volume, and gas particles are far apart compared to the other two states we just talked about. Gas particles move at a high speed in all directions. Um, I don't think we're going to cover gas laws in this unit, but one of the ideal gas laws is that all gas particles will move at high speeds in all directions. So yeah. So this is a little chart to help you between shape and volume. So a solid has a definite shape and a definite volume. A liquid has a definite volume, but not a definite shape. And a gas has no definite shape nor definite volume. So we're gonna go with two questions just to like make sure you understand it. Um, you guys can answer in the chat if you want. What state of matter is shown in this illustration? A, gas, B, liquid, C, plasma, or D, solid? Just type your answers in the chat and maybe explain why if you can. Yes, that is correct, Jessica. The answer is A. The particles in a gas are much further apart than those in a liquid or solid. So, yeah, you're right. Next question. Oh, I don't know why it says 3. I can't count. Which is composed of particles that have enough energy to move past each other, but not enough to break away from each other. So, ice cube, lemonade, oxygen, or water vapor. Again, type your answers in the chat and feel free to use an explanation if you can. Um, all right, since nobody said anything, the answer would be B, lemonade, because lemonade is a liquid, right? And as I said before, liquids have enough energy to move past each other, but not enough to break away from each other. So yeah. So now we're going to talk about periodic trends real quick. This unit is pretty straightforward. You either get it or you don't. It just depends on like what type of learner you are. But like if you have a good understanding of like atoms and the shape of atoms, you should be fine. So we will be comparing the shapes of atoms in order to figure out which elements have a higher ionization energy, electronegativity, and atomic radius. So we're going to very quickly talk about what these are. Ionization energy is the amount of energy required to remove an outer electron. So as we know, electrons have different shells. No, I mean atoms have different shells. And there's like electrons in each of those shells. So ionization energy is like the amount of energy you need to like remove an electron in the further outest shell. Electronegativity is the ability to attract an electron in a chemical bond. So like how easy the atom can like take in another electron basically. An atomic radius is pretty straightforward. It's basically like how big the atom is, or like how big the radius of the atom is. So the atomic radius, we're gonna start with that because it's the easiest. It's basically the radius of the atom. It is determined by how many shells an atom has. However, if they have the same amount of shells, because as we learned before, elements in the same period have the same amount of shells, right? So the atom with more electrons is actually smaller. This is because the more electrons the shell has, the more attracted to the nucleus it is. And because it's like more attracted, it's smaller, basically. Yeah, because stronger attraction means like shorter distance. There's actually a law about that. It's like between physics and chemistry. I would put it up here, but like you don't really have to know it. It basically just like explains why this is true. It explains why a stronger attraction creates smaller distance. So if you look at the periodic table, you can see here francium has the largest atomic radius because it's got the most shells. It's got 1, 2, 3, 4, 5, 6, 7 shells, and it only has one valence electron. So the attraction between the furthest electron and the nucleus is very weak, and there's lots of shells, therefore it's got like the largest radius. However, helium all the way over here, it only has one shell and it's got two electrons, two valence electrons basically. So they're all like it's tightly packed together, and it's got the smallest atomic radius out of all the elements. Actually, yeah, it does. Okay, so ionization energy. Um, it's, as we said before, the amount of energy required to remove an outer electron. So what makes it easy to remove an outer electron? It's got to have more shells, which means that the outer electron is further away from the nucleus. And the less outer electrons there are, the easier it would be. Like if there were two outer electrons, that'd be easier than like removing one of the five. Like taking one of the two is easier than taking one of the five, if that makes sense. Therefore, elements in the bottom left have lower ionization energies because they have many shells and fewer outer electrons, or as we just learned, they have the larger atomic radius. Therefore, it requires like less energy to remove the outer electron. Elements in the top right have high ionization energies because they have less shells and more outer electrons. So it would take a lot of energy to remove the outer electron. So, oh, I don't know why it's so blurry. But helium, everything is so compact. So taking away one of those electrons would be hard because like the force of attraction between that electron and the nucleus is pretty big because it's all like right there. But if you look at like francium again, for example, it's really easy to take its furthest electron because it's like 7 shells away from the nucleus and it's all out there alone by itself. So it would take very little ionization energy to remove one of the outer electrons from francium as compared to any other element. So electronegativity, it is basically the ability to attract an electron in a chemical bond. The smaller the atom is basically, the more exposed the nucleus is. Therefore, electrons from like a different atom will have an easier time being attracted to the nucleus of this atom. So, I forgot to put like a picture in here, but it's like basically the same trend as ionization energy, and it's the opposite of atomic radius. So here, watch, if we look up hydrogen Bohr model, right? Actually, let's use a different element. Let's look up helium. I forgot to put a space. But yeah, look at this. If an, like, I don't know why, okay, whatever, I'll just go here. If another electron wanted to like basically like join this element, it would be pretty easy because the nucleus is right here. It just has to like float near it, and then there would be like a pretty strong force of attraction. But if you looked at like francium's Bohr model, then you see how complex that is? There's so many electrons, and if another one wanted to join, there would be like a very, very weak force of attraction between that electron and the nucleus because there's so many shells and so many other electrons. Therefore, like, therefore, smaller atoms have higher electronegativity. So if you look at this chart, it basically combines everything we just talked about together. Where up here, this element, helium, would have high electronegativity and high ionization energy, but a small atomic radius. But all the way over here, francium, it would have a very large atomic radius, but a very small electronegativity and a small ionization energy. All the rest of these, you don't really have to know, like electron affinity, metallic character, and non-metallic character. You guys will learn about that in more advanced levels. But yeah, basically that's it. I was gonna dedicate the rest of this class, half of it to review these other units that we've already learned about. So just tell me in the chat which ones you want to go over or which ones you have questions about, and we can go over those. Like, what the heck? What? Okay. Yeah, just tell me in the chat what unit you want us to go over. Okay, since no one's saying anything, do you guys want me to just go over a random unit, or do you want me to just end the lesson right here? Just use the chat feature, or just turn on your microphone, please, so we can do what you want. All right, I guess we can do a quick review on the previous lesson, which was bonding and stoichiometry. Or actually, no, it's balancing equations and moles. Stoichiometry, basically. So, as we learned last time, a chemical reaction, atoms and their masses are always conserved, and the conservation of matter that comes into play here because atoms can't be created nor destroyed. They can only be rearranged. So in a balanced equation, the number of atoms on each side, the number of elements like in the reactant should be equal to the number of atoms in the product. So if hydrogen combines with oxygen to make water, this is not balanced because there's 2 hydrogens on the left and 2 oxygens on the left. And there's 2 hydrogens on the right, but only 1 oxygen on the right. Therefore, it's not balanced because there's not the same number of atoms on each side. So in order to balance it, you have to place coefficients in front of the reactants or products. You can only change the coefficient and you can't change the subscript. So this wouldn't be acceptable because it's not balanced. This isn't okay because you can't put a coefficient in front of the element itself. But this is okay. This works because if you count it, there's 4 hydrogens, 2 oxygens, 4 hydrogens, and 2 oxygens. And the coefficient is in front of the whole compound, not just an element. So the steps to balancing equation again is you list the elements, you count the number of atoms each element has on each side, you determine the coefficients, you check it, and yeah, it's a trial and error type thing sometimes, so use a pencil. If you take this for example, you list the elements, chlorine, sodium, and bromine. You count how many there are on each side. There's 2 chlorine here, 1 sodium here, and 1 bromine here. On the other side, there's 1 chlorine, 1 sodium, and 2 bromine. So what do you do to balance it? Well, you just multiply, you just like determine the coefficient. So now there's 2 sodiums and 2 chlorines. And if you added 2 on the other side right there, there would be also 2 sodiums and 2 bromines. Now they all have 2, and it's balanced. See, 2, 2, 2, 2, 2, 2. That's all good. This is another practice problem. You list the elements, you count it. Then you determine the coefficients. You multiply just like you recount it, basically. And then you add more coefficients to make it more balanced. And now you check, are there 3 magnesiums on each side? Yes. Therefore it's balanced. 2 aluminums on each side, it's balanced. 6 chlorines on each side, it is balanced. Make sure to multiply the coefficient by the subscript. Yeah. I think you guys have the gist of it since we talked about it last lesson. A lot. Okay, so we're gonna do a quick review on moles as well. So the units we're gonna use here. Wait. The units here are grams, molar mass, which is grams per mole, or AMU, atomic mass unit. Again, counting the molar mass is super easy. It's on the periodic table, so oxygen would be 16, O2 is 32 because it's 16 times 2, NO is 30 because it's 14 plus 16, and NO2 is 46 because it's 14, which is nitrogen, and then 16 times 2, which is O2. So you get 46. Other units we'll use is moles and particles. So finding the molar mass for these should be fairly easy because they're all on periodic table. And you can like use your calculators to like add it up just to, like if there's a compound and there's multiple elements. So these are the answers for those. This is mole conversions. So if you want to find the amount of moles that 7 grams of nitrogen has, nitrogen's molar mass is 14 right here. And the problem states that there's 7 grams. 7 divided by the molar mass would be 7 over 14, which equals to 0.5 moles of nitrogen. So in 10 grams of calcium, how many moles are there? You can see here that calcium's molar mass is 40. So you would do 10 divided by 40 to find out that there is 0.25 moles of calcium, and that's equivalent to 10 grams, okay? So this is particles. How many moles of nitrogen are there, and how many particles are there if there's 3.5 grams? So you would do 3.5 over 14, 3.5 over the molar mass, multiply by this number right here to find the number of particles. So you would find that first 3.5 divided by 14 is 0.25. So that's how many moles of nitrogen there are. And you multiply it by this number right here, and there's 1.5 times 10 to the 23rd nitrogen particles in 3.5 grams of nitrogen. That's a lot of particles. Okay. Now, 0.75 moles of calcium. How many grams are there? So you would multiply it by the molar mass. 0.75 times 40 equals 30 grams of calcium. So now you want to find the particles. It already gives you the amount of moles, so all you have to do is multiply it by this number again to find that there's 4.5 times 10 to the 23rd amount of calcium particles in 30 grams of calcium, or in 0.75 moles of calcium. So that was your homework from last time. That was your quick review on balancing equations and moles. So I guess that's it for today. Yeah, goodbye.